So much. Yes, I'm very I've benefited a lot from your seminar series, so I'm super happy to have a chance to present in this series. Um, sorry. I'll explain today the paper that appeared just 2 weeks ago or so with Alessia Mishosha and Fyodor Popov from Stony Brook. Um, So the paper was inspired by some recent developments by the collaboration from uh, Tata Institute. So Anand, let me just write the names. Benjamin, Kumar Minwala, uh, Mukherjee, Pal, and Rahman. So there was a recent paper where they posed some very interesting questions. They posed essentially some new conjecture about thermal physics, and we got very excited when this came out, and we wrote a paper believing that we have proven that conjecture. And actually, there were some interesting spin-offs that we were able to derive. And some older work in the same subject is by Benjamin Oguri Lee DSD. So there is a slightly older paper by Benjamin Oguri Lee and David Simon Duffin, who is very closely related questions about thermal physics of conformal field theories. Anyway, for what I'm going to explain, there are two ways to think about it, and I'll try to go back and forth sometimes between the two ways of thinking about it. And at any point, stop me with questions. Otherwise, I'll be talking to myself, which would be utterly boring. So, okay, let's begin. I'll just explain what the question is. So let me try to, is the screen updating? I've just scrolled down. I see that it's not updating for some reason. Or is it just a small delay?
Now we see the screen scrolling and
Yeah, I see. I see it now. I
so
just wasn't, mine wasn't syncing. Okay, so let me explain um, very generally what the idea is. I'll explain very generally what the idea is, and then I'll show you what we have done. So the general question, if you want the most general, sorry, the most general version of the question that we want to study is that we take a quantum field theory, we take some quantum field theory which may or may not be conformal, and we want to understand the spectrum of highly boosted states. So we want to consider time evolution with the operator h minus p, where the coefficient sp importantly is just 1. And in general quantum field theory, to understand the spectrum of h minus p is a very, very difficult problem. Think about massive quantum field theory because h minus p has contributions from arbitrarily many particles, which are very boosted. If you take many, many particles and you just boost them, you're gonna make the energy approach the momentum. And h minus p doesn't have a gap, and the problem is very strongly coupled, and for probably 50 years, if not more, maybe starting from the work of Weinberg, but maybe even earlier than that. We basically don't know much about the low-lying spectrum of h minus p. We don't understand very well the density of states. We don't understand this. We don't understand the interactions. A remarkable fact is that in conformal field theory, the problem simplifies if you change the question a tiny bit. So if you go to conformal field theory, there is an analogous question which leads to vast simplifications. So let's say, just for concreteness, to explain what is the simplification, let's go to 2 plus 1 dimensions. That's just the simplest case because there is the space is the smallest possible without making it completely trivial. And instead of talking about h minus p, we're talking about delta minus j1, where j1 is going to be the cartan of the SO3 rotation group in Euclidean signature. If you want, you can also think about it in Minkowski signature by writing delta minus m plus minus. Okay, it's the same thing. It's up to analytic continuation, the same thing where m plus minus is the boost generator in some space-like direction, and J1 is the rotation along some axis. Okay, these are the same things up to Minkowski continuation. So it turns out that this problem is much nicer. This problem is much nicer, and in the last 15 years, we have understood the spectrum of low-lying states uh, when the energy is measured with respect to delta minus J1. So delta minus J1 is often denoted by the twist, tau. We call that the twist. And let me just summarize what we have learned about the spectrum of arbitrary conformal field theory with twist. So the typical picture is that, like in flat space, you expect that there will be states which are extremely high energy states, so states with very large delta or very large J1, but they have a very small delta minus J1. So that's very similar to H minus P in that context, but it's much better than H minus P because we actually understand what's going on. So if this is the spin and this is the twist, we often see that there are operators that look like that. So they approach some constant. And then there are operators that maybe look like that, approaching some other constant. And there are just many, many of them approaching various constants. And these are the Regge, we call that the Regge physics, right? This is sometimes called Regge physics in conformal field theory. Sometimes it's called light cone bootstrap. Sometimes it's called analytic bootstrap. There are many names to this topic of understanding these particular operators. Now, how do we construct these operators? The construction is the following. You start from any primary operator. Let O be some primary operator, which we would put at 0. And let's start acting by derivatives of this operator. We will act with derivatives in the, let's say, plus direction. Plus will be some particular light cone direction. And we could do that m1 times, and then we could act with on the same operator m2 times, and we could do that all the way to mn. Okay, so usually in conformal field theory, such huge composite operators receive very large corrections to their scaling dimensions. And to first approximation, we don't know anything about such general composite operators. But in this particular case, if all the mi's are very large, and I'll explain what large means in a second. If all the mi's are very large, we actually know the scaling dimension exactly. So the scaling dimension is going to be n times the scaling dimension of the original seed operator. That's this n. So like the n operators just add up, and then we have a contribution from the scaling dimensions coming from the derivatives, where I goes from 1 to n. And there are very small corrections. Sorry, it's not the same O. There are very small corrections that behave in many examples, roughly speaking, like 1 by m. I'll be more precise about the nature of these corrections, but they behave roughly speaking like some powers of 1 by m. So if you take the m to be the largest parameter, then essentially you get free partons. This is a picture of free partons. Or sometimes you can think about it as some kind of asymptotic freedom, because large angular momentum is conjugate to small angles. So usually we have asymptotic freedom at short distances. Here we have asymptotic freedom at small angles in some very crude sense. Okay. Okay, so we know that such operators exist. And if you just do the algebra, you'll find for these operators, which are sometimes I'll call them Fock space operators, because they look like free partons and they furnish some kind of Fock space. For these operators, you can easily check that delta minus J1, which is the twist, as I said, is just n times the twist of the seed operator. So indeed, all these derivatives in the plus direction cancel out from the twist because they have the same scaling dimension and spin. And so you see the twist is additive. You can think about it as additive. and it's just indicative of weak coupling. Okay, the twist is additive and then it's indicative of weak coupling. Okay, so we know more or less everything that needs to be known about operators with very small twist in arbitrary conformal field theory in 2+1 dimensions. And now there is one question that comes up, one question that you can ask, which is very important, and it was asked only recently. A question that you can ask is, to what extent can we trust this Fock space? So can we really say that these operators behave like free fields with arbitrarily many derivatives and arbitrarily large little n? So is there some point beyond which the partons already don't behave like free fields? And the answer is yes, because there are small corrections, as I said. But I wasn't very careful in telling you how these small corrections look like. These small corrections have some complicated dependence on little n. They have some complicated dependence on the actual spectrum of low-lying operators in the CFT. And you can estimate of when this free Python picture will break down when these corrections start overwhelming the leading order contribution. Okay, so it's like asking, can we trust the quark model for protons made out of 1,000 quarks? Maybe at that point we cannot anymore because the small numbers add up and you get strong interactions if there are many, many particles. Actually, the same is true even in atoms. Electrons and protons are weakly interacting, but when you construct atoms with 60 electrons, we don't have a good analytical control on the orbitals, and it's more or less a phenomenological field. So the same happens here. And it turns out that you can trust the large spin expansion or the analytic bootstrap results or the Fock space picture. I'll just write the result. Trust the Fock space picture. You can trust the Fock space picture all the way to tau, which is of order square, all the way to twists, which go like tau to the power of j1 to the half. So it turns out that when the twist becomes of order of the square root of the angular momentum, the Fock Fock space picture breaks down, and the system becomes unwieldy. So we cannot use the conformal bootstrap anymore, at least not currently, to analyze the spectrum. Okay, so this is like the strong coupling scale. You can think about it. Okay, let me just rewrite this equation. You can define this scale to be the strong coupling scale of the twist. So when the twist becomes of this order, you get strong coupling. So that means that you cannot take the number of partons to be too big. Remember that the twist scales linearly with the number of partons for small number of partons. So that gives you some kind of constraint on how many partons you can consider before it becomes strongly coupled. Okay, so that's more or less what we know from the bootstrap. Are there any questions about it? Okay. By the way, this is verified in Monte Carlo simulations and numerical bootstrap very well. We see the Fock space. I don't know if we have already seen numerically that this is the breakdown scale. I don't know if this scale was seen in numerics or like in the numerical bootstrap, but maybe it was. I just don't know. Okay. So then,
So
yes.
maybe I can quickly ask, so how do you see that this is the breakdown scale
Yeah. So
analytically in Bootstrap?
yes. So it's a good question. I was skimming over it. Basically, you have to do one very difficult calculation, but completely straightforward conceptually, which is to use the bootstrap to calculate these corrections in the regime where you completely trust these corrections. So when you do this little calculation of the corrections, you'll see that the numerator has some power of n. And then you say, okay, I'm not going to trust this whole formalism when the corrections become comparable to the leading order contribution. But you must perform one non-trivial calculation of these corrections. If you want to see this calculation done systematically, you can consider a very nice paper recently that show the details. One is by Fitzpatrick, Fardelli, and Lee. Another is by Krafft and Mann. And you can see these corrections fully and rigorously. In the past, I had a paper with Gabriel corrections, some simple intuition, and the right answer, but for the wrong reasons. So they actually have the correct answer, and you can look it up. We got the right answer somehow by some miracle. The argument was not solid. It was just a handy argument to try to estimate these corrections. Okay, any other question? Okay, so what the okay. So uh, so we can consider the next question we'll consider is somehow people have said this particular function is so this particular partition function is extremely sick. There are lots of operators with the exact same twist. Just for instance, consider so essentially all the descendants have the same twist as the primary seed. And therefore this partition function without further regularization doesn't make sense. And we're going to regularize it in the following way. We will add minus epsilon times beta times J1. Okay? We're gonna try to regularize the partition function in this way. What does it actually do? It means that the evolution Hamiltonian is not quite delta minus J1, but we change the evolution Hamiltonian to delta minus 1 minus epsilon J1. And now we're not rotating at the speed of light anymore, so to speak. And we expect that these descendants will not contribute all the same, and we expect that the partition function will converge. Mathematically, to be more precise, uh, if we try to understand the partition function, we can put any epsilon we want, and there are two interesting values of epsilon, which are 0 and 2. And as long as the epsilon is between 0 and 2, the partition function must converge absolutely, I believe, just because you're rotating essentially below the speed of light, and here it's absolutely convergent. So here you should get absolute convergence. But when you take epsilon to 0 or 2, you're rotating counterclockwise or clockwise at the speed of light, and the partition function ceases to converge. And so the main question that we want to understand is what is the leading singularity as we approach this critical points epsilon equals to 0 or epsilon equals 2. Okay? So this question is dominated by operators which are spinning very fast and they have somewhat small twist. And this is what was the topic of the discussion recently, to try to understand how it behaves with epsilon. So I'm so far just reviewing what was done in recent months. Are there any questions about this version of the problem? Okay, so the conjecture that was put forth by the papers that I mentioned at the beginning is that the singularity is exponential. So they basically said, I'm going to switch to conventions that are more the conventions that will be like our conventions, but it's the same content. So they essentially said that there is a non-trivial function of beta plus corrections, and that this is the answer, that it's exponentially singular, where epsilon sits in the denominator, and f of beta is some unknown function. Okay? So why is the singularity exponential? It's very clear from the Fock space, because operators with many derivatives give you the same twist. And then when you start compounding operators in this Fock space construction, they all give you the same twist. So there is a huge, huge divergence when epsilon goes to zero. And if you just stick in the Fock space answer, this is a small consistency check that you can do. If you just use the Fock space ansatz, you will see immediately that this exponential of 1 by epsilon. So the fact that there is an exponential divergence is compatible with the Fock space. And what was done in recent months is to also show that it's compatible with thermal effective action. So this is the small temperature limit. In the small temperature limit, we can use the Fock space picture. And in the large temperature limit, we can use thermal effective action, and you get the same answer. You get the same exponential singularity, albeit with, of course, different prefactors, different functions of beta. So there was some evidence that this is true, that this exponential singularity is true, and they put forth this conjecture that that's actually completely general. Okay. The last thing I'll say before I switch to explaining why this conjecture is true and why this conjecture is so interesting, I'll just say one last thing, a final comment before I switch to something to explaining why this conjecture is interesting. The final comment before is that you can ask which operators actually contribute to these particular partition functions. Are these just the light cone bootstrap operators, or do we also get contributions from Fock space states with a very large little n? And it turns out if you do you have to do a Legendre transformation between the macrocanonical ensemble and the microcanonical ensemble. You just take this partition function and you ask which microcanonical states contribute to it. Yes, you just take this and you ask which microcanonical states contribute to it by doing a Laplace transform or a Legendre transform. And what you'll find out is that the states that contribute to this partition function at low temperatures are just the light cone bootstrap states. But in general, you also get contributions from states where tau is of order square root of j. So the reason that we call the paper Regge's Inferno is because it goes beyond Regge theory. It goes into the regime where this light cone bootstrap becomes strongly coupled, and that's why it's beyond light cone bootstrap. If you really want to understand this exponential singularity, you cannot use the light cone bootstrap in and of itself. That will only give you the low temperature limit. To understand this partition function in this where you take epsilon to 0 first, you also need to understand something about strongly coupled states where the twist is large. So that's why we call the paper Regge's
Can I ask
Inferno.
a question?
Sure.
About this function f of beta, do we only know the two limits for beta large and beta small, or do we also know if it's analytic in beta or other
Excellent
properties
question.
like that?
Excellent question. Let me respond to that. So the question is, what do we actually know about f of beta? From the light cone bootstrap, we know the low temperature limit, as you anticipated. And f of beta is exponential of minus beta tau min. And if I remember correctly, there is a beta squared in the denominator. That's for beta much, much bigger than 1. Sorry, that's the low temperature limit. That's what follows from the light cone bootstrap. Notice the order of limits. It's very important to memorize it. This tells you the leading order answer when epsilon is the smallest parameter. We just take this partition function and epsilon is the smallest parameter. It's in some sense the new double scaling limit, where we take the spin to be very large, but the twist is finite in units of square root of j. I'll actually write it down. So it turns out that this partition function corresponds to a new scaling limit in conformal field theory, where the angular momentum goes to infinity, but the twist in units of the angular momentum is finite. And how finite, what is the value of this finite number? It depends on the temperature. So we always take the spin to be infinite. That's what epsilon goes to 0 corresponds to. And we do that first. That's the largest parameter. And then we take this combination to be finite. And whether it's large or small, it corresponds to the temperature. So at low temperatures, this combination is small. At high temperatures, this combination is large. So it could be small at large. At low temperatures, it could be small. And at high temperatures, it would be large. So essentially, we're discussing a new scaling limit in conformal filter in 2 plus 1 dimensions, of which the light cone bootstrap is a corner. And in that sense, it extends the light cone bootstrap. Anyway, so yes, what do we know about this function? At low temperatures, it's light cone bootstrap. At high temperatures, it's just some power of 1 by beta. Let me see, it's 1 by beta. I believe it is going to be 1 by beta squared. I'm just, yeah, I don't want to think about it right now. It's either beta squared or beta cubed. That's just from the thermal effective action. Yeah, it's beta squared, I think. Okay, so we know these two limits, but if you think about it as an analytic, if you think about it as defined in this way through a limit of an absolutely convergent series, there is actually no reason why this function should be analytic throughout beta. It could be that systems have phase transitions as a function of beta when you take this order of limits where epsilon goes to 0 first. So it could be that there is a phase transition between the light cone regime and the thermal regime. I don't know if it ever happens. I don't know if it happens in the Ising model. It certainly happens at large n, but large n has another large parameter, which is n, and we take n to infinity first. So I don't want to discuss large n systems here. In systems with finite n, it could be that there is a phase transition here. So it could be that the function here as a function of beta is non-analytic, but I don't know of examples at the moment.
Okay, thanks.
Yes. Okay, so this is what was done, and now I'll explain to you what we have, why we got excited about this and what we have done. So when you look at this formula, you are drawn to this 1 by epsilon. It looks like a formula from thermodynamics. It looks like this is some kind of emergent volume. It looks like somehow in the large spin limit, the system becomes the local thermodynamic system with some extensive behavior and just completely standard vanilla thermodynamics. And so what we wanted to say is that this formula therefore must be derivable by saying that we can calculate this formula on some emergent geometry. So there must be some geometry which essentially calculates this formula. Okay, so this is the leading assumption. So the party line is that there must be some geometry whose volume is infinite. We want a geometry with infinite volume so that epsilon is just like a cutoff. Because when we calculate thermodynamics in infinite volume space, the volume becomes like a cutoff. So we're looking for some geometry with infinite volume whose thermodynamics, where the pressure function is essentially, if you want, the pressure function is essentially f of beta. So we're looking for a system where this is the local thermodynamics. And now I'll show you the answer in 3 plus 1 dimensions and how we obtain the answer. So how to obtain the answer? So how we are obtaining this geometry? Now I'll explain in a couple of minutes how to obtain this geometry and prove the conjecture.
Sorry, Zohar, can I ask a question? Just maybe running forward. In a large n limit, if you first take the large n limit, is it known what this geometry will be?
Oh, the geometry that I'm going to propose is still going to be correct at large n. It's just that then it becomes the geometry of the boundary, right? Because we're talking
Yes,
about
yes,
quantum field theory living on this. This is not an
yes.
emergent geometry. I said the word emergent. I didn't mean in the ADS CFT sense. It's a
Mhm.
geometry that calculates this partition function.
And so this will be true even if you have n as the biggest,
Yes,
largest parameter, and then take,
yes,
and then I suppose one would have to find like the dual geometry in a sense or
yes.
something.
One will have to find the dual geometry. And we
Okay.
haven't done that, but there is one paper that has a geometry that seems to do the job yeah, there is a paper that almost does it from 15 years ago. I'll mention it soon. But
Ah,
in
okay.
principle, there has not been almost any research on finding the holographic dual of these geometries.
Mm-hmm.
So
Okay,
let me now
thank you.
explain how you find this geometry. Thank you, Manuela. So we know that the spectrum of scaling dimensions is obtained by quantizing a 2 plus 1 dimensional conformal field theory on the two-dimensional sphere, and then we have the time direction. What's the central idea? The central idea is very simple. We need to take very large spin because we're discussing small epsilon. Small epsilon is Legendre conjugate to very large spin. If you spin something extremely fast, as you know from being on a carousel, it's going to go to the largest possible distance it can from the spinning, from where from where the velocity vanishes. So these states are going to accumulate near the equator. So it's therefore very clear that we need to do some kind of limit where we take the sphere and look near the equator. A very important fact that we explain in the paper is that the wave functions have some typical size in the transverse direction. So they localize on the equator, but you cannot neglect the width of the wave functions in that direction. And it turns out that this is square root of epsilon. At the end, epsilon will disappear, you will see. The geometry will have no epsilon because we want epsilon to be a regulator. But when we take the limit, epsilon appears throughout, it just drops out at the end. So we're talking about something that rotates with angular velocity epsilon to the power -1. You're rotating with angular velocity epsilon to the -1, but your transverse localization turns out to be square root of epsilon. And then you take a limit of the geometry with these parameters, and you obtain the following infinite volume geometry. So we obtain the following infinite volume geometry. Okay. You obtain this 2 plus 1 dimensional geometry where x is a non-compact direction. So x is non-compact. It runs from -infinity to infinity. Y is also non-compact, but because of the component of the metric, y is also non-compact. Okay, but actually it is compact for all matters and purposes because you see the g naught naught is 1 plus y squared minus g naught naught is 1 plus y squared, and that gives you a gravitational potential. It's exactly like having a quadratic gravitational potential. So everything is confined in the y direction. You can do another conformal transformation to make it obvious that y is compact. Just rescale the whole metric by 1 plus y squared, and you'll obtain that the y direction is effectively compact. Okay, so this geometry is called the Brinkmann geometry. A Brinkmann geometry. It has non-zero curvature, and it describes plane waves in GR. It's sometimes called also a PP wave geometry. This geometry has many interesting properties that I'm going to run through in the next couple of minutes, and then I'll explain what does it calculate. So the first interest, okay, so I'll just explain where this coordinate comes from. X, the non-compact coordinate, came from the azimuthal angle on the sphere. Y, which is this direction which is compact, came from theta. So that's the direction where we had localization of order square root of epsilon. And notice that epsilon has completely disappeared. And this is exactly what we wanted. There is no more epsilon. So when we calculate thermodynamics of quantum field theory in this geometry, there will be just standard extensive. It will be just a standard extensive thermodynamics, and we'll have to cut it off by the volume of the geometry, and that's it. So epsilon will appear kind of an emergent way. So all we have to do to recover epsilon is to say that the volume of this Brinkmann geometry is 2 pi by epsilon. And that dictionary is valid regardless of which quantum field theory you are discussing. That's just the cutoff that we put, and that's it. Now, this geometry has many interesting properties. This geometry has a Heisenberg group of symmetries. So if you look at the isometries of this geometry, there are two
Can I
isometries.
ask you one question? Hi, Zohar.
Yes. Yes.
You said that the metric is like this, and you have a volume which is a cutoff. In which so volume is like a product of all those dimensions in, let's say, 3 dimension you are using.
Yes.
In which direction, how much in epsilon you are putting the cutoff for? Do you need to consider that, or it's an invariant of which direction you are cutting it off
So the
in what scale?
after a conformal transformation, the y
Uh-huh.
direction becomes essentially compact. And since
I see.
we're
Oh, that's
discussing conformal fields on this geometry, right? We're
I see.
discussing just
Yeah.
ordinary conformal fields on this geometry.
Uh-huh.
And the y direction is compact in the presentation. The y direction has infinite range, but it's essentially compact. And
Yes.
after a conformal transformation, it becomes manifestly compact.
I see. I see.
So this is essentially the x direction. If you want,
Oh, I see. Okay.
this is
Okay.
just Lx.
Okay. Thanks.
This is the
Thanks.
size of the x direction. That's where we put the cutoff, and
Okay.
that's it. Now, this geometry has a Heisenberg group of symmetries.
Yes, I see.
And therefore,
Yes.
the large spin limit has
Mhm.
has these symmetries that were not really discussed much before. These symmetries must underline the large. So the large spin limit or the
Mhm.
Regge limit has these isometries. This
I see.
geometry captures everything there is to be captured about the large spin limit,
Mhm.
and it has these isometries.
Mhm.
These
Okay.
isometries constrain the spectrum of quantum fields
Uh-huh.
on this geometry,
I see.
and it makes the spectrum sit in some very interesting highest weight representations of the Heisenberg group.
Uh-huh.
And we check that by quantizing some simple free fields and some weakly interacting fields.
Mhm.
What's the bottom line? The bottom line is that we can now use this formalism to prove the universality of the small epsilon limit as a small. There are many applications
Yeah.
here, but one clear application is that we can use this geometry to just prove universality, which was conjectured before. Why? Because the partition function of if the partition function of quantum fields on this Brinkman space must obey locality. So we just assume that there is local quantum field theory. So it has to be the exponential of the volume of the pp wave times some function of the temperature. This geometry has no other scale. So if you have a conformal field living on this geometry, just from locality, the partition function has to be the exponential of the volume times some unknown function. And this we identify with 2 pi by epsilon. And that's it. So this is exactly the pressure of the quantum field in this geometry. Okay, so by doing the scaling limit, we can clearly derive the conjecture. And we can see that it's just the pressure function of quantum fields on the pp wave. And we actually have a lot of consistency checks of that in the paper. We quantized various fields on this space, and we saw that it gives the exact same answer as the microscopic partition function, where you sum over all the primaries with this epsilon and you take epsilon to 0. It just matches on the nose. Are there any questions
Uh,
about 2 plus 1?
can I ask a question very, very, very
Yes.
quick? Like, in principle, if I understand correctly, the regulator that you use to construct the PP wave and the regulator that you introduced above when you computed the partition function didn't have to be the same. You used the epsilon in both cases, but should I understand this to be completely rid of any scheme dependence? Is it like the fact that the two regulators, if I chose another regulator, I would have got the same result, basically?
I think you nailed it on the nose. So when we introduced epsilon to regularize the sum over all the operators, it was just to get rid of the infinite degeneracy in the twist.
Yeah,
We could have done that probably in a million other ways. And the singularity would still be an exponential singularity.
yeah,
So this
okay.
geometry gives you yet another regularization, which is infinite volume versus finite volume. So infinite volume is like, this geometry gives you like yet another way of regularizing it. I
I see.
believe that any possible regularization of the sum over the twist would probably be the same when you remove the regulator and you just look at the leading singularity. So that's why it works, I believe.
Okay.
But the derivation is not a conjecture. We actually show that this is true with this particular regularization. So we actually calculate the corrections to the PP wave due to the exact regularization that I showed you before. And you can see that it all goes to zero in the infinite volume. That you see that it works like I said.
Okay.
But I
Thanks.
believe, yeah. So one interesting comment is that this geometry preserves supersymmetry. So when we quantized fermions and bosons on this geometry, we got the exact same spectrum. This is not what happens when you quantize quantum fields on the sphere, because the scaling dimensions of bosons and scaling dimensions of fermions are not the same. So supersymmetry does not commute with dilatation operator. But it turns out that supersymmetry commutes with the time evolution in the Brinkman geometry. And that's very interesting. We haven't explored the consequences of that, so it's just a small comment that I'm making. Now I'll get to the um, more involved topic of 3 plus 1 dimension. Yes.
Zohar, I have a comment
Yes.
or question. So in principle, you could have, so you can write down this co-moving metric before going to this Brinkman geometry. And then you can use in the co-moving metric, there will be epsilon, and you can use that epsilon in the co-moving metric and compute the volume in that co-moving metric. Then you would have also obtained the same result, right?
Yeah.
Like
so yes. Yeah,
that would also relate
that's
this
how we
epsilon.
obtained it.
Mhm.
Yeah, that's how we obtained it. We followed epsilon, we did conformal transformations until we got an answer that doesn't have the regularization anymore.
I see.
Yeah, so this geometry just directly captures the large twist limit, or it just directly captures spinning states, and time evolution in this geometry corresponds to the twist.
Mhm.
And yeah, it doesn't have a regularization in it anymore. I'll just say one thing in response to what Srideep said, because it's an important thing. You could have discussed this geometry. So you could just say, I don't care about this thermal partition functions. I want to understand what is this geometry good for, okay? So that's you could just take this point of view, and I'll just tell you what it does. In addition to commuting with supersymmetry, which is a side comment, it turns out that time evolution in this geometry is the same as delta minus delta plus m plus minus. Sorry, this is the twist. This delta plus m plus minus plus p minus, which is the same as p plus k minus plus p minus. So maybe this is a slightly confusing point. I'll take 30 seconds to explain it a little bit more carefully. So one way to arrive at this geometry is by doing some scaling limit and following this epsilon and trying to prove the universality of the partition function. Another way to arrive at this geometry is say, I don't care about this thermal physics. I will just write down this metric, and I can notice that this metric is conformally equivalent to flat space. So time evolution in this metric has some interpretation in terms of the conformal generators. And if you follow that logic, you'll find out the time evolution in this metric corresponds exactly to the twist. This is the twist. This is up to some similarity transformation. This is the twist, and this is some kind of regularization. So time evolution in this geometry is exactly the twist plus some regularization. And it's not the same regularization that we chose in the thermal background. It's just some different regularization. But as I said, every regularization is as good as any other, presumably. And you can just prove using the Heisenberg symmetry that this is non-negative and this is non-negative. And indeed, when you quantize the quantum fields on this geometry, you'll see that you get that the spectrum is the twist plus p minus. So this geometry doesn't have to be arrived from that procedure that I explained. You can just write it down and say that it measures time evolution with respect to the twist. A variant, if you want something even more clean, you can just remove the 1 from the geometry and write minus y squared dt squared plus dt dx plus dy squared. And then time evolution is just exactly tau. So this geometry just has exact time evolution being the twist. And when you quantize quantum fields in this geometry, you'll find that there is infinite degeneracy, because we know that there is infinite degeneracy from the descendants and the Fock space, etc. Okay, so there are 2 points of view. You can just start from this geometry and say it's a regularization of the twist, and I'm going to compute partition functions, or you can arrive to it by some scaling limit.
Thanks.
Okay. Now let me discuss 3+1 dimensions, which has a very important new twist and a very strong result that we were able to obtain from this logic. Are there any questions about 2+1 dimensions? Okay, now in 3+1 dimensions, there is a very important new twist. Remember that in 2+1 dimensions, when we discussed this geometry as arising as a scaling limit, we had states localizing to near the equator. This was in 2+1 dimensions. In 3 dimensions, we have a 3-dimensional sphere. A 3-dimensional sphere in 3+1 dimensions. And if we look at spinning states, they turn out not to localize anywhere. So let me explain it more carefully. When we discuss local operators in 3+1 dimensions, we have scaling dimension and 2 Cartan generators, J1 and J2. That's because the rotation group is SO4 and it has 2 Cartans. We can take various large spin limits. We can take J1 to be much, much bigger than J2, or we can take J1 and J2 to be much, much bigger than 1. Or we can take J2 of order 1. We can take various scaling limits. And we have a Fock space construction, exactly like in 2+1 dimensions. So I'll explain them kind of side by side, hoping not to cause any confusion. So if we discuss this limit, let's discuss this limit. This is the limit of one large angular momentum. Okay, that's an interesting limit where the twist can be defined as delta minus J1, and we can just forget about J2. We can take a limit of large J1 and delta minus J1 being small, and there is an interesting scaling limit where J1 goes to infinity, and tau by square root of J1 is finite. That's the exact same thing we discussed in 2+1 dimensions. It turns out to work also in 3+1 dimensions. And this limit behaves very similarly to 2+1 dimensions. In this limit, particles localize to some particular circle on the 3-dimensional sphere, and you can take a scaling limit. So there is a scaling limit, and you obtain some effective geometry, which is very similar to what I had before. I'll just write down the metric. And it has basically the same properties as what we had before. It's just that the y coordinate is replaced by d-2 coordinates, which are transverse to the plane wave. Okay, so what I want you to just take away from this is that the limit of one large angular momentum in 3+1 dimensions is easy. It corresponds to the partons localizing around one particular location in the geometry of the 3-dimensional sphere. You take the same scaling limit and you obtain an effective geometry. And it has some Heisenberg group of symmetries, which is very large. In this case, it will be in 3+1 dimensions, this will be H5, I think. It has a very large group of symmetries that underlies the large spin limit, and you can have a long discussion about it. A more interesting limit is to take both angular momenta to be large. With a fixed ratio and a twist, which is fixed in some new units, which are like that. This is the strong coupling scale when both angular momenta are large. So previously, the strong coupling scale of the Fock space construction was when this is order 1. Tau by square root of J is order 1. When both angular momenta are large, the strong coupling scale is when tau by the combination is large. And the conceptually new ingredient that we encounter now is that the particles don't localize on any particular trajectory on the S3, and the scaling limit becomes much more interesting and complicated. Okay, I'll just write down the answer and I'll say a few words about it with the final conclusion, and and that's it. So tau here is delta minus J1 minus J2. So we define a new notion of twist, which is appropriate to the situation that both angular momenta are large. In this case, there is no localization, but you can still obtain an interesting metric, which is the following. So we obtain the following geometry that I just wrote down. And it has some Heisenberg group of symmetries. Again, there is an interesting Heisenberg group of symmetries. There is SO2, and there is time translations. And now I'll maybe get to one of the main points of this discussion. There is again a long story. You can quantize quantum fields. You can obtain the scaling limit of the partition function. I don't have time to explain any of that, so I'll just focus on one final point, which is maybe the strongest result spin-off of the paper, which I unfortunately won't have time to explain much more detail. This geometry has a global time-like killing vector. It's a causal geometry. It's a causal geometry. It has no ergosphere. It has a global time-like killing vector. And in fact, you can obtain this geometry by going to some rotating reference frame in the previous geometry that I wrote here. You can go to some rotating reference frame here and obtain the geometry that I just showed you. And just from causality, it follows that the spectrum is non-negative. Okay, so the spectrum IDT is non-negative. And that leads to a unitarity bound, which is the tau is bigger than 0, where the twist, I remind you, is in this case is delta minus J1 minus J2. So just from the fact that we found the geometry that calculates this notion of a twist, delta minus J1 minus J2, and the geometry is completely healthy. It has no ergosphere. It has a good causal structure, and quantum fields on this geometry should behave causally. Just from that fact, we obtain a new unitarity bound in 4 dimensions. People have tried to prove it using the null energy condition, and some special cases are known in the paper of Cordova and Diab. There is a nice paper that discusses this unitarity bound from a few years ago where they tried to use the null energy condition. But we obtained maybe a weak result that it's bigger or equal to 0. We don't know if it's bigger or equal to 2, for instance, but we've just obtained the weak result by causality. And so it resolves this interesting problem about the spectrum of conformal filters in 3+1 dimensions. In addition, just the symmetries of this geometry lead to the universality of partition functions. We obtain in this case 1 by epsilon 1, epsilon 2, where epsilon 1 and epsilon 2 are the regularizations of J1 and J2 in the partition function times some function of beta. And there are many, many other consequences of this approach. And finally, before I close for questions, I'll make one final remark, which is that you can again just forget about thermal physics and you can say, I just want to study this geometry because of whatever reason. And you will find that, again, this geometry, all it does is to describe the Hamiltonian, which is delta minus or plus m plus minus plus m12 plus p minus. So it's a regularized version of the twist. And that's essentially why it appears in the scaling limit. And that's why it has a good spectrum with no degeneracies. And it captures the thermodynamics in the large spin limit. And causality in this background implies that this combination has to be positive, and this is positive. And that's essentially like a summary of the main results of the paper.
So I have a question. So is there
Yeah,
any
so
way to...
I'm basically done. Thank you. If there are any questions, I'm happy to answer them now. I was very fast at the end, so.